Good morning to everybody. Welcome to the Master Transfer course. Today there will be lecture 5. So in lecture 4 we discussed about three things. One is concentration. We have seen the mass concentration, weight fraction, molar concentration, mole fraction, and we denoted mole fraction for the liquid phase xi and for gas phase, that is yi. Then we have seen average velocities. There are three. One is volume average velocity, molar average velocity, mass average velocity, and we have seen that molar average velocity is equal to your volume average velocity. And thereafter we discussed the fluxes. Flux, there are two types. One is mass flux and another is molar flux. And relative to the reference of frame, mass flux is three category, that is stationary to the observer, that is small ni, relative to an observer moving with the mass velocity, small ii, relative to an observer moving with the molar velocity, small ji. And for molar flux, relative to three reference, there are capital Ni, capital II, capital J. Although there are total 6 types of fluxes, but in general, in our mass transfer calculation, generally we use the molar flux, moles per meter square second or kilomole per meter square second. Generally, mass flux we don't use, but sometimes it can be used. There is some transport process where mass flux is used. Okay. And in molar flux, two things are very important relative to an stationary observer, and that is the Ni, capital Ni, that is N type of flux, that is the total flux, N type of flux, and relative to an observer moving with the molar average velocity Ji, capital Ji. This is also, what does it mean? It is mean that there is a flow, there is a average molar velocity, and which species will have a higher velocity than the molar average velocity, that is this is ui, the velocity of the particular species which has a higher velocity than the molar average velocity. So if this is that much high is there, and then that flux is Ji. That means if a particular species has much higher velocity than the molar average velocity, that is the capability of that molecule or species, and because of that, because that particular species or particular molecule has the higher velocity, they will separate first. So J type of flux is the capability of a particular species compared to the average, and N type of flux, Ni, that is the total flux. When somebody is standing in stationary reference, and when somebody is measuring how a particular species, then what is the flux, total flux, that is N. Okay. But separation point of view, that J type of flux is important. If some particular molecule has higher J flux, that molecule will separate first. But for design purpose, N type of flux is important. Total number of molecules are important. Okay. Today, these things we discussed in last lecture. Today we will develop a generalized equation for the molecular diffusion. And what will be that equation? Because first I told that we are interested to calculate the flux, because I know if flux is high, then I will get the better separation with smaller equipment. So always my objective will be to increase the flux as much as possible. Okay. Now, for mass transfer, there is one basic law is there, fundamental law, that is Fick's law. Fick's law. It is very much similar to your Fourier law in heat transfer and Newton law in fluid dynamics. What is Fourier law? So Fourier law is applicable for conduction. Conduction means medium is stagnant. So Fourier law states that conduction of heat flux is proportional to the temperature gradient. So you have studied this. This is the flux joule per meter per second or watt per meter per second. Then Newton law of viscosity for momentum transport, that is shear stress in a viscous fluid in a laminar motion. Keep it in mind, Newton law is applicable for laminar motion, can be shown to be equivalent to the flux of momentum from a faster moving layer to the adjacent slower moving layer. The Newton's law of viscosity states that the shear stress of the momentum flux is proportional to the velocity of it. That means tau zero x equal to mu s. So K is thermal conductivity, that is a proportional constant for Fourier law, and for Newton mu is viscosity, that is kg per meter square. This is, and tau is force per unit area Newton per meter. Similarly, in mass transfer, the basic law of molecular diffusion is Fick's law. What is about this law? This law states that the molar flux of a species, relative to an observer moving with the molar average velocity is proportional to the concentration gradient. Again I am telling, this law states that molar flux, so keep it in mind, molar flux of a species, and what is the frame of reference? Relative to an observer moving with the molar average velocity. So frame of reference, observer moving with molar average velocity. What does it mean? If you see here, that means relative to a molar flux and relative to an observer moving with the molar average velocity, that is capital J type, Ji equal to Ci into Ui minus C. So that law indicating only this flux, not other. Okay. And this for this now, if for a binary mixture, if I have a two component system A and B, then if A diffuses in a binary mixture of A and B, then according to Fick's law, flux of A, that will be Ja. Okay, J instead of Ji, that will be Ja is proportional to dCA by dZ, that is the concentration gradient, or Ja will be minus dAb dCA dZ. Okay, here dAB is the proportionality constant, and which is called diffusion coefficient or diffusivity, and J the flux, that unit is kilomole per meter square second, and dAB will be meter square second. Here if you can see there is a negative sign, it is the concept same as your Fourier law of heat conduction or Newton's law, because that dCA and dZ is negative, and flux we convert that is positive, to make it positive, the sign is there. Okay, so law is very simple, but keep it in mind, the statement of this law, it is the molar flux and relative to an observer moving with the molar velocity. That's why here I am writing capital J is proportional to dC. Now with this fixed law, we will develop one generalized equation for molecular which will be applicable for all the cases. So here fixed law expresses the molar flux J with respect to an observer moving with the molar average velocity. However, the molar flux Na means the molar flux with respect to stationary observer, Na with respect to stationary observer is useful for design and operating purpose. J is this is the capability. If J is high, means it is easy to separation. From design product, we are interested to measure the total molar flux. Okay, and expression of Na can be developed. How will I do this? Now we know molar average velocity U equal to this summation of Ci ui by summation of Ci equal to 1 by C total concentration into summation of Ci ui. We know this one, and also we know that molar flux relative to an stationary observer Ni equal to capital Ni equal to Ci ui. Already we have studied. Now for a binary system means two components, ethanol water mixture, and here I should mention that in our mass transfer study, mass transfer 1 and 2, we will discuss about only the binary system, because binary system is the most very simple system, because here we are developing the basic concepts. So we will not consider at this moment the multiple component system. Actually, if you see fractionation of petroleum crude, it is multiple component system. But as we are discussing the basic fundamental concepts of mass transfer, we will keep our discussion for binary system, and later there is a advanced mass transfer course. If you study further, there is a advanced mass transfer course, there will be multiple component systems will be discussed. But in this here we will keep our discussion for the binary system, always A and B. So if that molar average velocity U, okay, for this binary system, U will be summation of Ci ui, in this case 2AB Ca ua plus Ca ub by summation of Ci, that is Ca plus Cb. Sorry, this will be Cb. This will be Cb. Okay. U equal to CAUA plus CBUE plus C, total concentration of C equal to CA. So for binary system, my molar velocity will be this expression, and my total flux Na, that will be, because NiCiUi, that in this or system or component A, that would be Na equal to Ca plus UA. Na equal to Ca into UA, and similarly for Nb it will be Cb into UB. So now, so we from previous slide we got U equal to this expression, U equal to CAUA plus CBUB by capital C, N type of flux Na equal to CAUA, and Nb equal to Cb plus U. Now J equal to this, we know this one, because if you see that expression of Ji equal to Ci into Ui minus U. So in this case Ja will be Ca into Ua minus capital U. So if you see this, I have written this one, J from our J equal to Ca into Ua minus capital U. And from Fick's law we know J equal to this, isn't it? So now this equal to CAUA minus C into capital U. Now what is capital U? Capital U equal to this. Okay, so Ca by C, capital equal to CAUA plus CBUB by C, and this is equal to, now this is coming minus DAB DCA DZ equal to Na. Now what is this? CAUA, that is equal to Na. So this is coming Na minus this Ca minus C, CAUA equal to Na, CBUB equal to Nb, CAUA equal to Na, CBUB equal to Nb. Now if you rearrange this, means if I take Na, so Na, if you take this here, Na equal to Ca by C minus DAB DCA DZ. Okay, so if you take this term, this whole term here, this side, then it will be this minus this, and that will be your expression of Na. So this is the generalized equation for the molecular flux. So N type of flux means total flux. N type of flux when observer in a stationary phase. Okay, that is the total flux equal to Ca by C plus Na plus Nb minus DAB into DCA by DZ. Now what is this term? This is nothing but your J according to Fick's law. Okay, so total flux, in total flux there are two components. One is this contribution is coming from the molecular diffusion, that is the capability of a particular species, means if that species, how much higher velocity that species has compared to the molar average velocity. And this term is representing the contribution of the flux because of bulk flow. Okay, because of this bulk flow is happening, and that is the contribution. So So Na, capital Na equal to Ca by C plus Na plus Nb, the okay, minus DAB dCA by dZ. This is the generalized equation of molecular diffusion. What most probably you have studied the generalized equation in reaction engineering. Okay. Similarly, there is a generalized equation in mass transfer. You have to keep remember this equation. This is very important equation, basic equation. Not only you should remember this equation, how this equation is coming from fundamental concept, you should practice it. If you do practice in pen and paper 10 times, you will see it will be with you. So total flux equal to, there are two contribution. One contribution is coming from the bulk flow and another contribution is coming from the molecular diffusion. This is just like I can give you one example. Okay, but let's check you went to one cinema hall to watch some movie. Okay, now when shows will be off, then what will happen? All people will try to come out. When all people will try to come out, that means there is a average velocity. But among this crowd, will one maybe the more energetic who will push the other people and he will come out first. So who is the more energetic and he will come fast, means his flux is high because of this stuff, because he pushing the other people aside and he is coming fast. There is one flow is there already because of the average flow of the crowd that is there, but this guy, one guy is more energetic, that's why he has better contribution and that's why his flux is. But if somebody, let's take, does not have any more energy, whatever the crowd will come, he will come. So what will happen? Then this term will be 0 and he will come, that flux will be this. And if it is coming, that see in mass transfer point of view, you cannot separate it because he is with a common people. Who is coming first? That means you can separate them. Okay, he is coming fast, so it is. And somebody is slower than the thing, then he may take more time, that will be in the opposite position. Okay. Similarly, in mass transfer, one is for the bulk flow, that is the, in cinema hall, that is the common flow. Okay. There is a average flow is there, because of this flux is coming, and this flux is coming because of molecular diffusion, means somebody has a higher velocity than the average velocity. Okay. So this equation is very important, but keep it in mind, we express this equation in terms of Ca, concentration, molar concentration. Now already we discussed that there is a molar concentration, and generally we do not use the mass concentration, hence rho I and corresponding W, but molar concentration, and when it will be the gas phase, okay, then generally gas phase the concentration is expressed in terms of partial pressure. And also number of cases where it is very common, the people are expressing the concentration in terms of mole fraction. Then for gas phase it will be Yi, and for liquid phase it will be X. But here I express this equation, generalized equation, in terms of molar concentration. So it will be better. So we should know, if let's say if you have a problem in terms of where concentration is expressed in terms of mole fraction, then you have to convert this equation in terms of mole fraction. Or in a gas phase system, if the concentration is expressed in terms of partial pressure, that means you have to convert this equation in terms of partial pressure, and this is very easy. Let's see. So this is my equation. Na equal to Ca by capital C, Na plus Nb minus dA by dC by dC. Now for gas phase, Ca will be Pa by Rt and total concentration C will be P by Rt. Now for this equation we have in terms of molar concentration. So Ca equal to Pa by Rt, C equal to Pa by Rt, Rt will be cancelled out. So Pa by P, Na by Nb, and this dCA equal to dPa by Rt. So then it will be this. So in terms of partial pressure, the expression will be this. Okay, and so we have in terms of mole fraction. So we have this in terms of molar concentration. Now we derive this in terms of partial pressure. Now what is Ya? Ya equal to Pa by P. Okay, so Pa by P I am putting is Ya, and dy equal to dPa by P. So Pa equal to dy into P. So dA by Rt P. So this will be in terms of your mole fraction for gas phase, because here pressure term is there. Okay, because in gas phase total pressure will be available to you. But now if you convert this in terms of liquid phase, now what is Ca? Ca equal to Xa into total C. Okay, so Ca by C will be Xa, and total C, let's say this is the total C. Okay, and dx by this. And what is total C? Total C is total concentration. Okay, that will be molar concentration, and this is the mass concentration. Okay, or density of the solution by average molecular weight. So Na will be Xa minus dAb into C, capital C, dxa dz, isn't it? So today what we have studied is that just we have derived the generalized equation for molecular diffusion, and that we express in terms of concentration, in terms of partial pressure, in terms of mole fraction in both gas phase and liquid phase. Okay, so this is all about for today. Thank you for your attention.